Hello everyone, hope you are doing very well. So as you all know that today we are going to cover the chemical kinetics chapter, and today is the day 1 of this chapter. So let's start our topic. NCRT chapter 3, chemical kinetics theory part 1. First of all, disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concern or issue, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using the generative AI, which is experimental. So, first of all, let's discuss the important thing that how to prepare for the chemical kinetics chapter for your competitive exams like JEE and NEET. Okay, so wherever this chapter holds in the examination as a syllabus, how you can prepare for this chapter particularly for your competitive exams. First of all, you should understand the syllabus of this chapter. Okay, and the percentage of the syllabus which is coming out in your particular examinations. So basically, different examinations holds the different percentage of various chapters, that how much the percent of the particular chapter is coming or is covering in that particular exam. So you should first of all know or understand the syllabus. So check the official syllabus for your exam. Focus only on the topics which are included in your exam. So basically, first of all, you should know about your exam, and then you should know about the syllabus, the official syllabus of your exam, and what are the topics from the particular chapter. For example, here we are talking about chemical kinetics. So in the chemical kinetics, what are the topics that are included in the exam syllabus? Only try to focus on that particular topics for the preparation of that particular exam. Next thing you have to cover is that key concepts or key topics to cover. What are the key topics uh, that are already holding the syllabus of the examination? You should know about those key topics. Like if you talk about here in this chapter, the key topics first of all are rate of reaction. In the rate of reaction, we will cover the average and the instantaneous rates or units of rates also. And then we will talk about the order and the molecularity. So this is second key concept, order and the molecularity in the chapter chemical kinetics. Under this we will study about the difference between the order and the molecularity, that what are these and what are the difference between them and their examples. Then the third main topic under this chapter is rate law and rate constant. Okay, rate law and rate constant are interrelated, and in this we will study about the writing of the rate law. What is rate law? How can we write a rate law for a particular reaction? What are the unit of rate constant and for different order reactions? Then we will focus on the integrated rate equations. So for the zero, for the first and for the second order reactions, what is the integrated rate equations that comes in this chapter? So that is also a measure or a key concept. Then half-life. Half-life is also a key topic in which derivation and calculation for different orders of reaction half-life will come. And also we will talk about the pseudo first order reactions, and then temperature dependence, that how the temperature dependence is present in various terms in this chapter, that how different factors is depending on the temperature in which manner. In this we will talk about the Arrhenius equation, very important, and the activation energy, another important thing. And then we will talk about the basics of collision theory in the end of this chapter. Okay, so these are the key topics third you should study, or third you should focus for the preparation of chemical kinetics is study material. That means what are the study material that you are following for the preparation of your competitive exam. So first of all, you should know about the NCERT textbook. In the NCERT textbook, chemical kinetics chapter is present. So you should first of all cover the NCERT textbook for basics and the theory part, especially for the NEET examinations. Reference books you can also use, or you can also practice the reference books like OP Tandon, which is for the physical chemistry, and P. Bahadur for the numerical chemistry for the sufficient numerical calculations, and R.C. Mukherjee. This book is involving the physical chemistry again. And for the J examination, you can follow the Senge's book for the chemistry, or Willy physical chemistry. Okay, so these are the textbooks that we are suggesting you for the preparation of the particular chemical kinetics chapter for the competitive exam. And first of all, you have to focus on the NCERT textbook. Then you can apply, or then you can use the reference books for various categories of the chemistry, like physical, numerical, and Senge's is good for both theory and the numerical part. The fourth point you should do is make short notes and formula sheet. Also, while you are studying from the different books of different sources, you should make short notes whatever you are studying for the future reference or for the future learning or revision. And you should also have a formula sheet if you are, particularly if you are studying in physical chemistry. Write the key formulas, the graphs, and the concepts in a notebook for the quick revision. As I said, for a quick revision, whenever you want to, you can take your notes out and study the key formulas, graphs. You can see the graphs and the concepts. So that's why that we are suggesting that make the short notes and also ready a formula sheet for this particular chapter. Fifth thing you can do is practice numericals as much as you can, right, from the different reference books and the NCERT. NCERT is must. Solve ample numerical problems, as questions often involve the calculations. Okay, so that's why solve as many as questions as you can, because there is a lot of calculation, so you need to be handy in solving those calculations very fastly, right? And sixth point you can consider in the preparation of competitive exams is previous year questions. So practicing previous year questions is very important to know the pattern, that how your particular exam is repeating, or how the particular exam is giving the type of questions, and what is the pattern of the questions that are repeating or asking in that examinations. So go through the previous year paper and the sample questions to know the exam pattern. Seventh point is that mock test and time management. Also, you should practice. That means you should test yourself by giving the mock test, and you should know the time management, that how much time you are taking for solving a particular question or a problem. So take the chapter wise and the full length mock test before your actual examinations for the practice, for the good practice. Practicing solving problems within a time limit. Also put a time limit there, that you have to start from this time to and at this time when you are starting to solving a question paper, okay, or problems. So put a time limit. Within that you have to solve the problems, you have to practice the problems, and try to maintain this time limit, and try to minimize this time limit also. Eighth is revise regularly. So as you know that our brain has so many things to remember, to store, right? So to revise the particular thing which you have studied in the past is very, very important. So revise the formulas, exceptions, and the solved problems frequently to get in touch with the thing or with the content that you have already studied in the past, so that you will not forget anything and your hard working or your hard work will not go as waste. Okay, so that's why revise regularly whatever you are studying, the formulas, the exceptions, the solved problems even. Okay, let's talk about today's lecture. So the objective, after attending this lecture you will be able to define the average and the instantaneous rate of a reaction. Okay, so today's objective of the lecture is that after attending this lecture you can or you will be able to define the average rate of reaction and the instantaneous rate of reaction, and also you will be able to express the rate of reaction in terms of change in concentration of either the reactants or the products. Okay, so how can you relate the rate of a reaction with the change of concentration of reactants or products, that you will also able to understand after attending this lecture. So what are the topics that you are going to cover in this lecture according to the NCERT? First of all, we will talk about the introduction part, then the characterization of the chemical reaction, then we will talk about the conversion of diamond to the graphite, and then we will cover the section 3.1 of our NCERT textbook, which is rate of a chemical reaction. In this we will study about the rate of a reaction, the concentration change in the constant volume reaction, and rate expressions for different reactions, instantaneous and average rate of a reaction, mathematical representation of instantaneous and average rate of a reaction, rate expression for the stoichiometric reactions, and we will study then or we will see some examples from 3.1 to 3.2, and also then text questions from 3.1 to 3.2 in the end of the lecture. Okay, so let's start. First of all, let's start with the introduction part. So the characterization of chemical reaction. So a chemical reaction, so how can you characterize the chemical reaction? What are the characteristics of a chemical reaction? A chemical reaction can be characterized in the two ways. Thermodynamics, which tells us about the feasibility of a reaction, that whether that reaction will take place or not. Okay, so thermodynamics of a particular reaction will know or will tell us about the feasibility of that reaction or the reactants and the products. That means whether that reaction will happen, reaction will take place or not. Second, we will talk about the chemical kinetics, right, which comes under the characterization of chemical reaction, which decides that how fast, as the word kinetics means something is moving, right? We are studying about something which is moving. So chemical kinetics decide how fast or how slow the reaction will occur. The word kinetics is derived from the Greek word kinesis, which is meaning movement. Chemical kinetics is the part of the chemical science which is dealing with the study of rates of chemical reactions and the factors which affect the reaction rates, like concentration, temperature, and the pressure. So chemical kinetics is a part of a chemical science which deals with the study of rates of chemical reaction. That means in the chemical kinetics we study about the rate of chemical reactions and about the factors which will going to affect the reaction rate, for example concentration, temperature, and the pressure during the reaction. Conversion of diamond to the graphite process. So thermodynamic data indicate that diamond shall convert to graphite. Okay, thermodynamically, this is concluded that diamond shall convert to graphite. That means maybe we can convert the diamond to the graphite. But in the reality, conversion rate is so slow from the diamond to the graphite that the change is not perceptible at all. In the reality, the change will not happen because the conversion rate is very slow from the diamond to the graphite. By the way, let me tell you that diamond and graphite both are the allotropes of carbon element. Therefore, the most people think that diamond is forever. Okay, as in reality, in thermodynamic properties or in thermodynamic data, the conversion of the diamond to the graphite is possible, but in the reality that conversion process is so slow that this change is not perceptible at all. Therefore, most people think that diamond is forever. Diamond can will not going to convert into some another thing because that process is very very slow, right? That's why people think that diamond is forever. Now let's talk about our first uh, topic, which is rate of a chemical reaction, which is the section 3.1 in our NCERT textbook. Under this topic, some reactions such as ionic reactions occur very fast. So some reactions are occurring very fast, like ionic reactions. Ionic reactions involves the formation of the ionic compound. So for example, the precipitation of silver chloride, precipitation of AgCl occurs instantaneously by the mixing of aqueous solution of silver nitrate and the sodium chloride. Sodium chloride, that means this NaCl, when you mix it with the solution of silver nitrate, that is AgNO3, right? Silver nitrate, then there is instantaneous mixing of these two, and we will get the AgCl as a product, as a precipitate. Okay, so this reaction is a very fast, and this is a kind of ionic reaction. On the other hand, some reactions are very very slow. Okay, if some reactions happen at the higher rate, that means there are presence of another reactions, another type of reactions which occur very slow kinetically. For example, the rusting of iron. Rusting of iron process in the presence of air and moisture is the process which is a slow process, which occur very slow. So there are reactions like inversion of cane sugar and hydrolysis of starch, which proceed with a moderate speed. So there are some reactions which includes the cane sugar inversion, the hydrolysis of starch, which proceed with the moderate speed. Okay, so there are all the types of reactions, whether it can occur very fast or very slow or at the moderate speed also. Continuing on this topic, speed of a reaction or rate of a reaction can be defined as change in the concentration of reactant or the product in the unit time. Now, how can you define a speed of a reaction, that the reaction speed is this much? How can you determine that? How can you tell that to someone? So, for determining the speed of a reaction or rate of a reaction, both are same. Speed of reaction, rate of reaction, both are same. So if you want to know about the rate of reaction, you can define it as the change in the concentration of the reactant or the product in the unit time. That means in our reaction, how our reactant is changing with time, or how the concentration of the reactant or the concentration of the product is changing in unit time, that will be defined as the rate of reaction. Now, to be more specific, it can be expressed in the terms of the rate of decrease in concentration of any one of the reactant. Okay, that how the concentration rate, how the concentration of the reactant is decreasing. What is that rate of decreasing of the concentration of any one of the reactant? Or you can also express the rate of reaction in terms of the rate of increase in the concentration of any one of the products. If the in the reaction the reactant gets to utilize, that means the concentration starts to decrease for the reactant. For the product, the concentration starts to increase because the product starts to form in a reaction, in a chemical reaction, right? So you can define the rate of reaction as the rate of decrease in the concentration of reactant or the rate of increase in the concentration of the product. If concentration is in mole per liter, that means we are talking about the unit of the concentration. If unit of concentration is mole per liter and the time is in seconds, then the units for the rate of a reaction will be mole, liter inverse, second inverse, right? That means change in concentration divided by per unit time, right? Unit time. In the unit time, how much concentration is changing? So concentration unit is this much mole per liter, and the second, which is the unit of the time, which is already in the denominator, will go in the numerator and become -1. So second inverse. So this is the unit for the rate of a chemical reaction. In the gaseous reactions means the reaction where the reactant is present in the gaseous forms. When the concentration of gases is expressed in terms of their partial pressures, then the units of the rate equation will be atmosphere per second. Also, when you talk about the or when you take the gaseous reactions where the reactants and the products may be in the gaseous form, then when the concentration of gas is expressed in terms of partial pressure, not in the terms of moles per liter or something like that, but we are saying that the concentration of the gas is in the terms of their partial pressure. We are using the partial pressure to define the concentration of a gas. Then the unit of the rate equation will be atmosphere second inverse. That means the unit of the concentration into second inverse. Similarly, atmosphere second inverse. Okay. Now, concentration change in the constant volume reaction. Consider a hypothetical reaction. Now, let's consider a reaction assuming that volume of the system remains constant. The system have the volume which is a constant, which is remaining as constant. So, reactant is becoming the product. Now, when 1 mole of the reactant R produces 1 mole of the product P, now if R1, that means this, and P1, that means this, are the representation for the concentrations of the reactant and the product respectively at time T1, and R2 and P2 are their concentrations at time T2, then that means we are talking about the different concentration at different time for both reactants and the products. Then the delta T, that is change in the time in this during process, is equals to T2 minus T1, right? Because at T1 the concentration is something and at T2 the concentration changes, right? So the change in time will be this total time T2 minus the T1, right? This time between the T1 and T2 is the change in the time. So you can also say that change in the concentration of the reactant will be the R2 minus R1. Similarly, the change in the concentration of the product will be P2 minus P1, because finally P2 forms initially P1 we have. So P2 minus P1. The square brackets in the above expression, you can see we are using square brackets. They are used to express the molar concentrations. Okay, they are representing the molar concentrations that we are talking about, the molar concentration of the reactants and the products. Now let's talk about the rate expressions. The rate of disappearance of reactant. So if reactant is becoming product, that means reactant concentration is decreasing and product concentration is increasing. That means reactant is disappearing and product is appearing, right? So the rate of disappearance of reactant, or you can say the rate of decrease in concentration of reactant, will be equals to the decrease in concentration of reactant divided by the time taken. The rate will be equals to the concentration change divided by the time change or time taken in this process. Okay, so that will be equals to minus of delta R divided by delta T. Delta is representing a small change in the concentration of reactant, and here delta is representing the change in the concentration of change in the time taken or change in the time. Okay, so rate of a disappearance of reactant will be equals to decrease in the concentration of reactant divided by the time taken in that process. And this is the NCERT equation marked as 3.1 in our NCERT textbook. Now rate of appearance of P, that is product, that will be the increase in concentration of P divided by the time taken in that process, which is equals to positive delta P upon delta T. Okay, now if you see, okay, this is the NCERT equation marked as 3.2. Now if you see, the rate of disappearance of R has negative sign here and rate of appearance of P has positive sign. You know why? Negative sign because something is decreasing. The disappearance of R, that means R is disappearing. The appearance of P, that means the product is appearing. The concentration of the product is increasing. That's why we are using the positive. Since the delta R, that means the small change in the concentration of the reactant, is a negative quantity as the concentration of reactant is decreasing. As I said, because we are putting the negative sign because the concentration of reactant is decreasing. So the delta R is negative quantity. It is multiplied with -1 to make the rate of the reaction a positive quantity. You have to multiply it by -1, okay, to make it the rate of reaction a positive quantity. So equations 3.1 and equation 3.2 given above represent the average rate of a reaction, that is R average. Okay, so these are representing the R average rate of reaction. Now let's talk about the instantaneous and average rate of reaction. What are these? First of all, the average rate. So average rate is calculated over a period of time. Okay, average rate, we calculate the average rate over a particular period of time, over a period of time, providing a general idea of how quickly the reaction is proceeding. Okay, at that particular time, what is the rate over a period of time, what is the rate at which the concentration of the reactant in the product is changing, that is considered as average rate, which is calculated over a period of time, which provides us a general idea that how quickly the reaction is proceeding. Now it's often determined by finding the slope of a line which is connecting the 2 points on a concentration time graph. Now if we have a concentration time graph, the slope of a line which is connecting the 2 points on the concentration time graph, you can determine the average rate easily. Second type of rate is instantaneous rate. The instantaneous rate on the other hand focuses on the rate of a reaction at a single point in time. Now in time, at a particular point at a given time, what is the rate of reaction? So that is considered as instantaneous rate. It is equivalent to the slope of tangent line to the concentration time curve at that point. Now at that particular point, at that particular time on which we are considering the reaction. So when you draw the concentration and time graph or curve, then at that point, what is the slope of the tangent which is coming? That will be the instantaneous rate, which is representing the reactions rate at the exact moment. Okay, that will be the reactions rate also. Now mathematical representation of instantaneous and average rate of reaction. So what is the mathematical representation of these? Average rate. This is defined as the change in the concentration of A divided by the change in time duration, where the change in A is the change in concentration and change in T is the change in time, right? This is the basic definition or the formula for the average rate, for defining the average rate. Now instantaneous rate, which is defined as dA by dt, where dA is the infinitesimal change in the concentration, a small change in the concentration of A, and dt is the infinitesimal change in the time. How the time is changing, how a little change of time has happened, and what is that. So that you can put it here in the denominator. So this is the rate expression. Okay, there are two graphs in the figure 3.1, instantaneous and average rate of reaction we have given. So we have this concentration of reactants versus the time graph, where we have at the zero some concentration R naught for a particular you can say solution, or for a particular element, right? Now you can see that at various points on the curve you are defining the various values of the time and the reactant, okay, the concentration of reactant. So the R average, that is the average rate, will be the change in the concentration of the reactant divided by the change in the time. So this will be that R2 minus R1 upon T2 minus T1. Okay, R2 is this point and R1 is this point. R2 means we have some concentration of reactant. We have named it as R2, and if we have another concentration of reactant and we have named it as R1. So the slope, so the average rate is defined as minus of R2 minus R1 divided by T2 minus T1. Similarly, the instantaneous rate at a particular point is defined as minus of dr by dt, where this will be equals to minus of slope, right? Similarly, here it is given the graph between the concentration of the products and the time. Okay, the graph is again a different shape, this shape. Okay, now we have P1, P2, that is the concentration of the products, P1, P2, and the time value T1, T2, and T. Okay, here also you can define the R average, which is del P by del T, that is product change divided by the time change, which is equals to P2 minus P1 by T2 minus T1. Also here, if the graph is drawing as a quarter of a circle, then at the surface of the circle there is a slope going on, which is equals to the R instantaneous. So instantaneous rate will be equals to dP by dt. Okay, change in the concentration of the product divided by change in concentration of change in time. So these are the two graphs representing the instantaneous and average rate of a reaction. Now the rate expression for the stoichiometric reactions. Now let's consider a reaction which is mercury Hg plus Cl2 chlorine will form HgCl2, that is mercury chloride, where the stoichiometric coefficient of reactant product are same, right? Here is 1, here is 1, here is 1 in the multiplication in three of them, the reactants and the product, right? So stoichiometric coefficients of reactants and products are same, 1, 1, 1. Then the rate of reaction is given by, rate of reaction will be the change in concentration of the mercury with the time, which is also equals to the change in concentration of Cl2 with the time, and it is also equals to the change in concentration of HgCl2 with the change in time. So these are the rate of reactions for the rate, or you can say for the stoichiometric reaction. Continuing on this topic, consider a reaction. Let's consider a reaction in which 2 moles of hydrogen iodide decomposes. Okay, we have a reaction where 2 moles of Hi decompose to produce the 1 mole of H2 and I2. It means that 2 of Hi is decomposing to produce the hydrogen and the iodine gases. For expressing the rate of such a reaction, where the stoichiometric coefficients of reactants and products are not equal to 1, the rate of disappearance of any of the reactant or the rate of appearance of the products is divided by their respective stoichiometric coefficient. Now if you want to write the rate of such type of reactions where we have the Hi decomposing, 2 moles of Hi decomposing to their particular elements H2 and I2. So if you want to write the rate of such reactions where the stoichiometric coefficient of reactants and products are not equal. Here it is 2, here it is 1 and 1. So though they are not equal between the reactant and the product, then the rate of disappearance of any of the reactant or rate of appearance of any of the product is considered is divided by their respective stoichiometric coefficient. If you talk about the HI, so what is the rate of disappearance of HI, because HI is a reactant, divided by the respective stoichiometric coefficient, that means 2. Meanwhile, for hydrogen it will be H2 by 1, for I2 it will be I2 by 1. Since the rate of consumption of the HI is twice the rate of formation of hydrogen or iodine, to make them equal, the term delta HI is divided by 2. Okay, so we are saying that because the rate of the consumption of the hydrogen iodide molecule is twice the rate of formation of H2 or I2, right? To make them equal, the term delta HI is divided by 2. Okay, this delta HI for the HI product will be divided by 2. The rate of this reaction is given by minus half of delta HI by del T. So basically our reaction was 2HI giving us H2 plus I2, right? So what we are saying, that rate of consumption of the HI is twice the rate of formation of H2 and I2. That means if you are consuming 2 moles of HI, you are making 1 mole each of hydrogen and the iodine gas, right? So if you want to make them equal, that means the rate of consumption of the reactant and the formation of the product, the term delta of HI you will use, and it will be divided by 2, right? Now you can write the rate of reaction, which will be minus half of, okay, anything which is present in the stoichiometric coefficient of the reactant or the product, it will go in the product with the rate expression, and also in the denominator. So this here 2 is present with HI, so the rate of concentration change of the HI will be multiplied by minus 1 by 2, because it is the reactant we are talking about, which is decreasing. So this is also equals to delta H2 by del T. This is positive because product is forming, and it is also equals to delta I2, that is the formation rate of the I2 divided by delta T, right? So this is the rate of reactions for this reaction given. Continuing on this topic. So similarly, for the reaction, this, if you want to consider another reaction, let's say 5Br negative plus BrO3 negative plus 6H positive, it is giving us 3Br2. By combining this and this Br, 3Br2 plus 3H2 from this and this. Okay, there is 3Br2 and 3H2O. So rate for this reaction can be defined as minus of 1 by 5 of delta Br negative by delta T, and it is equals to minus of delta of BrO3 negative divided by delta T. It is equals to minus of 1 by 6 delta of H positive by delta T. It is equals to 1 by 3 delta Br2 by del T. It is equals to 1 by 3 delta of H2 divided by delta T. So this is the different rate expressions for the given particle provided reaction. Now for a gaseous reaction in the gaseous form at the constant temperature, the concentration is directly proportional to the partial pressure of a species, and hence rate can also be expressed as the rate of change in partial pressure of reactant or the product. Okay, so basically the concentration is directly proportional to the partial pressure, because at the place of concentration you can also use the partial pressures to determine the rate expression. So concentration is directly proportional to partial pressure of a species, and hence the rate can also be expressed as the rate of change in partial pressure of reactant or product, other than the rate of change in the concentration. Okay, now let's practice an example which is marked as example 3.1. So from the concentrations of C4H9 chlorine, which is a butyl chloride, at different times given below, calculate the average rate of the reaction. We have given the different concentrations of the C4H9 chlorine at different times. From these, you have to calculate the average rate of the reaction. So, reaction is C4H9Cl butyl chloride reacts with the water molecule, forms C4H9OH, an alcohol, plus HCl. This is during the different intervals of the time. Okay, not at the same time. So, this is the provided data that the time in the seconds is given as 0, 50 second, 100 second, 150, 200, 300, 400, 700, 800 second. And the concentrations of butyl chloride given at particular time, okay, is 0 0.100, 0 0.905, 0 0.0820, 0 0.0741, 0 0.0671, 0 0.0549, 0 0.0439, 0 0.0210, or 0 0.017 at different time interval. They are the concentrations of various concentrations of butyl chloride given. Okay, so what you have to tell? You have to calculate the average rate of this reaction given. So let's solve it. What we can do, we can determine the difference in the concentration over the different intervals of time and thus determine the average rate. Okay, how so average rate is basically the rate, or you can say the change of concentration at in the time interval. Okay, so we can determine the difference in the concentration over different intervals of time and thus determine the average rate by dividing the change of concentration over that particular time interval. It is given in table 3.4. So table 3.4, which is representing the average rates of hydrolysis of butyl chloride C4H9 chlorine. So this is the table 3.1. The concentration of the butyl chloride at T1. Okay, and so basically these are different things given. So this is the concentration of the butyl chloride at T2. This is T1 and T2 respectively. This is average rate, which is determined by minus of the concentrations of the butyl chloride at T2 minus the concentration of the butyl chloride at T1 divided by the change in the time T2 minus T1, the time interval. Okay, and multiply by 10 to the power 4 for the unit conversion. Now you can simply do that. We know the concentration at different times. We know the different times. You can find out the average rate by just applying in this formula. So this will be minus of 0.0905 because it is at T2 minus 0.100 divided by 50 minus 0, that is 50, multiply by 10 to the power 4. It will give out the first average rate as 1.90 over this interval T1 and T2, 0 to 50. Okay, so we just arrange the given seconds like 0 to 50 to 50 to 100, 100 to 150, 150 to 200, 200 to 300, 300 to 400, 400 to 500, and 700 to 800. Okay, so basically these are the time intervals which are already given in our question and their respective concentrations of the butyl chloride. Okay, so by simply applying this formula, okay, you can determine the average rate of the butyl chloride at different time intervals. This is how you can solve it. Okay, now let's solve the another example which is marked as 3.2. The decomposition of N2O5 in the CCl4 at this 318 Kelvin temperature has been studied by monitoring the concentration of N2O5 in the solution. So the N2O5 is decomposing in CCl4 at this particular temperature, and this has been studied by monitoring the concentration of this N2O5 in the solution. Now initially concentration of N2O5 is this much, 2.33 mole per liter, and after this time 184 minutes it is reduced, the concentration is reduced to 2.08 mole per liter. the reaction takes place according to the equation 2N2O5 giving us 4NO2 plus 1 oxygen molecule. Calculate the average rate of this reaction. This particular reaction for the N2O5, you have to calculate the average rate in terms of hours, minutes and seconds. What is the rate of production of the NO2 during this period? The rate of production of NO2, as we are getting the NO2 as the product. So during this period, what is the rate of production of NO2, that you also have to tell. Okay. So let's see how you can solve this example. First of all, you should know that for the given reaction, the average rate is defined as minus half change in the concentration of the reactant, that is N2O5, divided by the change in the time interval. You can also express it as plus 1 by 4 change in the concentration of the NO2 divided by del T, and it is also equals to change in concentration of oxygen divided by del T. Because in the product there will be positive, because it is increasing, the concentration is increasing quantity, and this is also the average rate, which is minus half, minus because the concentration of the thing is decreasing. This is a decreasing quantity. Simply you have to put the various values given in this formula. So minus half multiplied by change in concentration. So initial concentration was this 2.33, right? After 184 minutes, it is reduced to 2.08. Okay, so when you subtract these two and divide by the time that will take in this change of the concentration, and when you solve this fraction, it will be 6.79 times 10 to the power minus 4 mole per liter per minute. Okay, so this is average rate. You have to convert it into the hours and seconds also. So 6.79 times 10 to the power minus 4 mole liter inverse minute inverse. When you convert it into the hour, so multiply by 60 minute per hour, it will be 4.07 multiplied by 10 to the power minus 2 mole per liter per hour. So this is in terms of hour. Now in terms of seconds, you also have to calculate. For that, you have to take this 6.79 times 10 to the power minus 4 mole per liter per minute multiply by 1 minute per second. In 1 minute, there are 60 seconds existed, right? So it will be equals to 1.13 multiply by 10 to the power minus 5 mole per liter per second. So these are the values of the average rate in minute, hour and second. Now we have to answer that what is the rate of production of NO2 during this period. So for that, so it may be remembered that the rate is also defined as 1 by 4 of change of NO2 divided by change of time, right, as I said. So this quantity will be 6.79 times 10 to the power minus 4, and this 4 will also go in the multiplication, so multiply by 4, because this quantity is also equals to the minus half of N2O5 change divided by the delta T, remember, right? So this quantity is this much, 6.79 times 10 to the power minus 4. So this is equals to this, and this quantity will be equals to this quantity multiplied by 4, because this 4 will go in the multiplication at the right hand side. Understood? Okay, let me tell you again. So rate, previously we have studied that rate is equals to minus of half. That means the decrease of concentration of N2O5 divided by the change in the time. Okay, and this value of this rate is coming out as 6.79 multiplied by 10 to the power minus 4. Now we are also saying that this rate is equals to this rate, 1 by 4 concentration change of NO2 divided by del T. Okay, that means this value is equals to this value, 6.79 multiply by 10 to the power minus 4. So if you want to only find out the value of only this quantity, then it will be 6.79 into 10 to the power minus 4, and this 4 will go in the right hand side in the multiplication into 4. That's what we are writing it here. Okay. So it is coming out as 2.72 multiplied by 10 to the power minus 3 mole per liter per minute. Why we calculate this quantity? Because this is the rate of production of NO2. This is defined as the rate of production of NO2, which is equals to this much. Okay, so this is how you can answer this question. Okay, now let's see in text question marked as 3.1. For the reaction, reactant is becoming product. Concentration of reactant changes from 0.03 molar to 0.02 molar in 25 minutes. Calculate the average rate of reaction using the units of time both in the minutes and the seconds. Okay, if you are using the time unit in minute and second, then calculate the average rate for the given reaction. So let's see how can you solve it. Average rate of reaction is defined as in the terms of reactant minus of change in concentration of reactants divided by the change in time. You can simplify it and write it as minus of R2 minus R1, that is the second at the T2 time what is the concentration of the reactant, minus at T1 time what is the concentration of reactant, divided by the T2 minus T1. So as the concentration are given, so 0.02 minus 0.03 divided by 25 molar minute inverse, and negative is already present. When you solve it, this fraction, it will be minus of 0.01 by 25 molar per minute, and this minus will become plus. So this will become 4 times 10 to the power minus 4 molar per minute. You have to convert it into the seconds. Okay, because we have to give the answer both in the minutes and the seconds. So when you convert in second, 1 minute have 60 seconds, so divided by 60, because already minute is present in the denominator. Okay, so 4 into 10 to the power minus 4 in the denominator, 1 minute is equals to 60 seconds, so we put 60 at the place of 1 minute. When you solve this fraction, it will be 6.67 multiply 10 to the power minus 6 molar second inverse. So these are the values for the average rate of reaction in the minute and the seconds. Okay, so this is how you can answer this question. Let's see one more in-text question marked as 3.2. In a reaction, 2A reactant is giving us products. Concentration of A is decreasing from this concentration to this concentration in 10 minutes. Calculate the rate during this interval. Okay, this interval means in the 10 minute this concentration change is happening. So during this interval, what is the rate as per this reaction? So average rate, as you know, is defined in the terms of reactant as minus of the in the denominator the stoichiometric coefficient, which is 2 here in this case. So minus half multiply by change in concentration of reactant divided by change in time. We know the change in concentration, which is A2 minus A1 divided by change in time T2 minus T1. We have given both the concentrations at 2 times. So there, this will be minus of half 0.4 minus 0.5 divided by 10, because the time taken T2 minus T1 is 10 mole per liter minute inverse. When you solve this, it will be minus half multiplied by minus 0.1 divided by 10 mole per liter per minute. Okay, you just have to subtract these quantity. It will be minus 0.1 and rest are same. And now you have to solve this fraction. When you solve it, it is coming out as 0.005 mole per liter per minute. You can also write it as 5 times 10 to the power minus 3 molar minute inverse as the average rate of the given 2A2 products reaction. So for this reaction, the average rate is this much. Okay, so this is how you can calculate the given question. Okay, thank you so much for this chemistry session.